Hello and welcome back. Today I want to talk about linear regression. So linear regression is one of the most commonly used tools for making predictions in statistics. It's usually what's called a baseline method. So before you try any of your fancy techniques, you usually want to try a linear regression and see if it works because it's so easy to interpret, so easy to carry out, and has a long history of just working. So what I have here in the top left are the prices of Bitcoin on the x-axis and Ethereum on the y-axis. So as you might imagine, the price of Bitcoin is very closely related to the price of Ethereum. And what I've done here is carry out a line of best fit. And this line is fit by a method called least squares regression. So what I want to do is first give you the theory of how least squares regression works. Then we'll go over to a Jupyter notebook and carry it out. And then I'll come back and I want to get a little bit deeper into the theory, and that's certainly an optional section. You could have a good experience with this video just going through the first two sections. All right, so let's get to it. So first of all, what is regression? So given a random variable y and a covariate x, so that is like a independent variable x, regression is the process of deducing the expected value of y. So y is a random variable, but you might want to know where you expect it to land, given x. So a little bit more precisely, we want a function r of little x, which is going to give us the expected value of y, given that my measurement variable, big X, is equal to little x. So that's regression in general. Now, linear regression is a parametric model where we're not going to look at all such functions. Of course, there's a huge, uncountable infinite amount of them. We'll just look at linear functions. So in linear regression, we look at functions of the form r of x, so that's our regression function, is beta 0, that's our constant term, plus beta 1 times x. And this is supposed to be our expected value of y. Now, there's a lot of models for how you want to think about and how you want to carry out linear regression. I'm going to talk about the most common, most basic one first. So this is called the simple linear regression model. So the simple linear regression model is given by my outcome variable yi is beta 0 plus beta 1x, so there's a linear relationship, but there's this extra term, epsilon I, which you could think of as the error, and this error needs to have some properties. So the error is a random variable, and the expected value of this error should be equal to 0. There's like a true linear relationship. I think that one's fairly intuitive. But here's one that is maybe a little bit less intuitive. You want your variance of your random variable to be equal to sigma squared. And this is a single sigma squared for all epsilon I. So all of your errors have the same variance. Now, of course, beta 0 and beta 1 are not known at the outset. Otherwise, we'd be done. So we estimate beta 0 and beta 1 by, as usual in statistics, when you denote the estimators, you give the variables with a hat. Beta 0 hat and beta 1 hat. So how do we choose these beta 0 hats and beta 1 hats? That's the statistics part of all this. And well, as you might imagine, you should probably first look at your errors. So given that yi hat is r hat of xi, so this is our predicted value. Our residuals are, so this is the estimate of this epsilon I, which you could think of as like a noise variable. So you call it epsilon I hat. And it's equal to the true value of yi minus our predicted value of yi. So we're going to need to, in some way, minimize these residuals. And it turns out what the usual correct thing to do is to use the least squares estimate. So the least squares estimate chooses beta 0 hat, these are things we get to choose, and beta 1 hat to minimize what's called the sum of square residuals, SS res, which is the sum as I goes from 1 to n of epsilon I hat squared. So this may not be intuitive at first. Why are we squaring these? So let me give you some intuitive reasons. We square so that, first of all, plus and negative errors don't cancel out. So I'm going to have a line here, fit to some data. And of course, the line isn't going to fit straight to the data. Maybe I have an error, like an absolute error here of 2, and an error here of -2. Well, if I were just to take yi minus yi hat, we would say, oh, this line is a perfect fit. There's no error if we just add the distance between yi and yi hat. But when you square them, suddenly you will get, instead of 2 and -2, you'll get 4 and 4. So this has like a error of 8. So that's one reason. And the second reason is that more drastic errors are penalized heavily. So if you were just to add together, say, the absolute value of the errors, that's another thing that you can do and people do and is useful. But if you were just to do that, then an error of 4 is twice as bad as an error of 2. Whereas if you square them, then the error of 4 is 4 times as bad as an error of 2. Because you'll get 2 squared 4 versus 4 squared 16. So that's the intuitive reasons to use the least squares estimate. But after we go through setting everything up in Python, I want to say what happens more formally, which is that, so we have these error random variables, epsilon I, right? And we didn't make an assumption on their distribution. But the most common distribution found in nature is the normal distribution. If epsilon i's are normal, in particular they're normal 0 sigma squared random variables, then the least squares estimate, least squares, is the maximum likelihood estimate. And if you don't know what maximum likelihood estimate is, you could go ahead and watch my previous video, or just look it up. But I'll refresh that and we'll prove this after the break. Okay, so we want to find beta 0 hat and beta 1 hat, which minimize the sum of squares. Okay, that's a great lofty ambition. How do you do this? So in practice, we can find beta 0 hat and beta 1 hat by gradient descent. That's a topic for another video, but essentially you could look at your SSRes, the sum of squares of residuals, and it turns out to be a differentiable function. And when you have a differentiable function, you have an idea of where to move to start to make things smaller. And if you continue to move in the direction that makes things smaller, you eventually land in a minimum, at least in this case. So that's what you do in practice. But it's interesting to note that we can solve for beta 1 hat and beta 0 hat explicitly by beta 1 hat is equal to the covariance of x and y divided by the variance of x. Okay, so let's just look at this formula for a second here. Proving this is a bit involved, but at least intuitively, this can start to make some sense. The covariance of x and y is how x and y change together, and then you want to scale that in some way, and you scale it by the variance of x. And beta 0 hat, after you've computed beta 1 hat, you could find it to be the mean of your y data minus your computed beta 1 hat times the mean of your x data. Okay, so we've gone through, we've fit a line to our data. Now, there's sort of two sides to making a model in statistics. One is creating the model, and the second is evaluating how good the model is doing at explaining your data. And the explanation I want to use here, there are many, but the one we'll talk about today is called the coefficient of determination. So goodness of fit can be evaluated using the coefficient of determination. And this is typically denoted r squared. Okay, so what's r squared? Well, let me remind you that the residual sum of squares is the sum as I goes from 1 to n of yi minus yi hat squared. And so this is kind of like the sum of square of your errors. And now I'll also introduce SS tot, sum of square total. And this is essentially the total variance of your variable you're trying to predict, so the y. So the sum as I goes from 1 to n of yi minus y bar. You take the mean and you subtract off all the data points, and then you square that. This is the total amount that y varies in some sense. Now, this r squared, the formula for it is 1 minus the sum of square residuals divided by the sum of square total. So when you see a formula like this, try to think about the extreme cases. So if my sum of square residuals equals 0, what happens? R squared is equal to 1. So if R squared is 1, that means my sum of square residuals is 0, which means that my line had no error at all. So R squared is equal to 1, very good fit. Now, if my sum of square residuals is equal to my sum of square total, that implies that R squared is equal to 0. So when does this happen? So compare SS_res and SS_tot here. If you have y bar for every yi hat, in other words, you always guess the mean of your y data, then SS_res is equal to SS_tot. And that's sort of the absolute baseline data. You just guess the mean of your data. Okay, so the takeaway here is that R squared is equal to 1 is a very strong correlation, and R squared is equal to 0 is a very weak correlation. All right, so let's move over to the notebook and let's see how to implement all of this in Python. All right, so here we are in the notebook. So I'm going to be using a couple libraries here. I'm going to be using pandas to read in and manipulate our data. I'm going to be using matplotlib to plot some stuff. I'm going to be using scikit-learn for carrying out our linear regression and for evaluating it. So the linear regression is an sklearn.linear model, and the R squared coefficient of determination is an sklearn.metrics. Let's go ahead and import all those in. Okay, so I have on my computer a couple CSVs containing Bitcoin prices and Ethereum prices. You could get them for yourself at these links on Kaggle. Let's go ahead and read them in and see what we're working with. So I want BTC, my Bitcoin prices, to be pd.read CSV. So let's read in. I have this saved as btcprices.csv. And let's see what we are working with. Okay, so I have this data frame, and it has a date, it has the price, and then it has a bunch of stuff that I could be useful, but for what we're going to be doing right now, we don't need. So I want to drop all that stuff. So I want to do BTC dot drop, that drops columns, and I just have copy and pasted over here just to save a second. The columns I want to drop open, high, low, vol, and the change percentage. Now I'm going to do this, I'm dropping columns, so you want to do axis equals 1, and I'm going to do this in place. You have to be a little careful when you do things in place. You can't do it twice, but hopefully we can be careful here. And the second thing I want to do is the price column is currently a string, and I want this to actually be a linear regression. Linear regression needs numbers, so I need to get that string to be a float. This is pretty standard stuff, but let's see how you do it in pandas. We could say BTC of price is equal to BTC of price, and then what I want to do is go to the string library and replace. So we're going to replace the comma in there by nothing. So first argument is what you're replacing, second is what you're replacing it by. And then I'll still have a string, but without the comma. This is good. Python can understand that as a digit, so we want to pass this as type float. And then let's go ahead and take a look at the head again and make sure we got what we want. Great. So now we have dates and prices. Now let's do the same thing for Ethereum. So I am going to have ETH is pd.readcsv. I think I have this saved as ETH prices. Yep, there it is. And this data, thankfully, the person preparing this data did a very good job at standardizing everything. It's formatted in the same way as the BTC data frame. So let's go ahead and just copy and paste what we did there, replacing the BTC by ETH. So there's that. And let's just make sure we are good there. Okay, so there we go. Those are the Ethereum prices. And now what we're going to do is take these two data frames and stick them into one data frame. So I'm going to call this data frame merged. And Pandas has a method called merge. And I'm going to merge BTC with ETH. And so, one of the columns is date and price. You could merge on either of those hypothetically. You tell it what to merge on with the on parameter. So on date. So now I will have a data frame where the dates match up. And here is a bit of a kicker. I have two columns named price here. So to give them unique identifiers, Pandas has a argument called suffixes, and I want to give my first price the BTC suffix and my second price the ETH suffix. Okay, and if all that goes well, let's sort the values here by the price BTC. That'll be the name of the price column. So I'm going to sort this by the price of Bitcoin. That'll just make our linear regression easier to understand. And we'll do this in place. Wonderful. All right. So before we go ahead and just do the linear regression, you should just eyeball your data. So let's just go ahead and make a quick scatter plot. So PLT, that's my matplotlib, scatter, and I have my merge data frame, and I will have the X be the price BTC. The Y is going to be the price ETH. And let's give it some labels. The X label will be the BTC price. The Y label will be the ETH price. And then let's go ahead and show this. Let's see what it looks like. All right, so there it is. And as you can see, there's a pretty reasonable linear relationship there. So here's another little trick. The dots are just like a little bit too big. We have a huge amount of data points. There's an extra parameter called S, which is the size of your dots in a scatter plot. And let's go ahead and set that to something smaller, maybe 10. There you go. You can get some distinction there of the points. Maybe even 7 will be better. Yeah, that's a nice looking scatter plot. Okay. So like I mentioned, in the simple linear regression model, you usually want your variances to be fixed about the line. Here you can see the plot like scatters out more as you go farther right. That's not that's a bad thing for linear regression, but it's not be all end all. You just have to be more careful if you're computing things like p-values and the such. We could still get a very meaningful model out of this. Okay, so let's go ahead and get our regression line. So here's how this works in sklearn. First, you call a generic linear regression model, and then we're going to eventually do some fitting. So for our fitting, we're going to need x's and y's. So this is a bit of a technical point that you'll get used to as you use these things more. The regression line wants a particular shape of data, and the right thing to do here is to reshape this. -1 tells it to infer the x amount of shapes, and then 1 tells it to make a one-dimensional array at the end. And now we are good to fit. So we'll fit the x data to the Ethereum prices. And let's go ahead and get our predictions also. So this already makes you a regression line, and then predictions will be equal to regression line dot predict of x. So this will give me my line. Okay, so let's see all that runs well. Great. Let's go ahead and plot everything out. So first of all, I want to have my scatter plot again. And I also want to have my regression line. So you can plt.plot x's, my y's are the predictions. So predictions, you feed it in, you can feed it in an array like we did, x, and it'll give you an array of y. So now I have x and y points. Let's just make that color red. Let's also have our labels as before, x label and y label. And then let's show this plot, see what we got. There we go. So didn't take that long, a couple minutes, and you have a regression line, and you can start to make predictions. And just for fun, let's go ahead and compute that r-squared coefficient of determination. Very easy to do. We'll go take our regression line, we'll score it, x, and merged price. So the regression line already has the y values in, and then you give it like the like true y values. So I want price ETH, and that should give me back our squared coefficient of determination. And there it is. And for what it's worth, that's typically considered a very good r-squared score. It's sort of hard to interpret it outside of a particular domain, but in pretty much every domain, 0.88 means very closely related. So we can conclude that Bitcoin prices explain, it's not causal, but they explain a good amount of the variance in ETH prices. All right, so the last thing I want to do is show you that the least squares line is actually also the line that maximizes the likelihood in the situation where the errors are normally distributed. So here we are. I have our goal written out there, and I'd like to recall some facts. First of all, if I have a normal mu(i) sigma squared random variable, that's the probability density function there. Should look familiar. Let me also remind you from before that the simple linear regression model is that yi is beta 0 plus beta 1 xi plus epsilon I, with the expected value of epsilon I being 0 and the variance of epsilon I here being sigma squared for every epsilon I. And we're going to be maximizing likelihood. Remember, likelihood is just what you get when you have a probability density function and you plug in all your values in there, multiply them all together, and that's your likelihood. So using this, let's see if we can deduce this result. So first of all, let's note that under the assumption of normality for epsilon I, we get that yi is a random variable and it's distributed like, so beta 0 plus beta 1 xi, that stays fixed. So the randomness part just comes from epsilon I. Epsilon I is going to be a normal 0 sigma squared random variable. So the mean of it, the mean of yi now is going to be at beta 0 plus beta 1 xi. So it's a normal beta 0 plus beta 1 xi sigma squared random variable. So again, you're basically just taking your epsilon I, which is a normal random variable, and then adding to it beta 0 plus beta 1 xi. So you just shift it over, and yi becomes this random variable. Okay, so now let's go ahead and look at the likelihood of the data. And the likelihood of yi given xi is, okay, so let's give this a name. It's the likelihood. And we're going to have beta 0 and beta 1 to play with. Remember, we're fitting this line, so you get to move it around. And it's also going to involve this sigma, which we're not really going to get to play with, but that's fine. Well, what I have to do is plug in my yi values to the predicted, or like the essential yi values, which would be beta 0 plus beta 1 xi. So just to make this a little easier, I'm going to express a proportionality here. I just don't want to keep writing the square root of 2 pi. So, well, sorry, this is the product as I goes from 1 to n of f of yi, y given x, of yi, and given xi. This is going to be proportional to, so I plug in my yi's into those probability density functions, and I will get, so there's going to be n of them, and I have a 1 over sigma, so I'll get sigma to the minus n, and then I'll get a bunch of products of e's. So just to simplify this, I'll write this as exponential, so it's e to the minus 1 over 2 sigma squared times the summation as I goes from 1 to n of yi, that's the observed value, and the data we're fitting it to is a normal beta 0 plus beta 1 xi normal distribution. That's the center of it. And we're going to square that. Okay, so that's a little bit tricky to work with, as likelihoods typically are. And usually what you want to do is take the log likelihood. Remember, log is an increasing function. So if we maximize the log of this function, we'll maximize the function itself. So then the log likelihood is given by so usually denote this little l of beta 0, beta 1 sigma, and I just take the log of that up there, and we'll still get this proportionality. I will get minus n times log of sigma. That's the first part. There's a product there, which becomes a summation, and I'll get minus 1 over 2 sigma squared times the sum as I goes from 1 to n of what's inside there. So yi minus beta 0 plus beta 1 xi squared. So beta 0 plus beta 1 yi, so this is minus n log sigma, so all of this I'm going to keep the same, except this I'm now going to call it yi hat. That's our predicted value for yi, and I'm trying to minimize this function, and it turns out what I need to do is choose beta 0 and beta 1, that's all I have control over, to minimize this summation here. That summation here is exactly the residual sum of squares. So this is the residual sum of squares. So minimizing the, let's trace through it, minimizing the likelihood, maximizing the likelihood is the same thing as maximizing the log likelihood. The log likelihood has this minus thing here with a positive number. So I want to minimize this red portion here. So maximizing the likelihood is same as minimizing the sum of squares. So maximizing, let's summarize that. Maximizing likelihood is minimizing the residual sum of squares. And there we have it. Least squares is the maximum likelihood estimate in the case where the errors are normally distributed. That's all I have for you today. Thanks, and I'll see you again next time.